Okay, here we go. All right. So, quick introduction. So, my name is John Gross. I'm the owner and mechanical engineering lead at JM Gross Engineering, based in Texas here in the U.S. And the purpose of this presentation is to go over a case study for a project that I've been involved in really kind of off and on for the last 10 years for a client of mine, where we started with their existing enterprise data center with air-cooled ITE, and through a series of projects, we've gone through and added some liquid-cooled ITE to that facility. And this presentation is about some of the challenges that we ran into and some of the interesting things that popped up as we dug deeper and deeper into that deployment. So the existing facility, like I said, it's an enterprise data center, air-cooled ITE, hot aisle, cold aisle, perimeter CRAHs, served by a campus chilled water. So this data center resides on the owner's campus, and they have a campus-wide chiller plant and distribution center. And during the design of the air-cooled data center, we did lobby to get our own dedicated high-temperature plant, and we lost. So they hooked us up to their existing or to the chiller plant that they were building as part of that campus, which operates with a supply water temperature of 5.5 degrees C. So we do have containment overhead, and we're going through the operation of the facility. We're about 5 years in, and management comes in and says, "Hey, we're going to bring in our HPC. We've been co-loing our HPC at a couple of different locations, and the prices are going up, and we want to bring it all in-house under one roof." And so this is kind of where the jumping off point was for this activity. So can't share who the client is, but the location is in climate zone 2A, so hot, humid, and all the issues associated, all the challenges associated with that. As I mentioned, we're on a multi-building campus. The data center is actually the closest building to the chiller plant on the campus distribution system, which will become more important as I get deeper into this discussion. So as I mentioned, the existing workloads are enterprise-based. They're running anywhere from about 5 to 10 kilowatts per cabinet. Nothing out of the ordinary for the enterprise market. The HPC workloads that we were bringing in were such that the first generation of equipment was going to be operating at roughly 90 kW per cabinet. The data center was originally designed and built to be expandable, and the way that we did the expansion is that we provisioned core and shell space in the structure to accommodate additional floor space to be built out in the future. One of the nice parts about that is that it did allow us to physically separate the liquid-cooled ITE and the HPC equipment from the air-cooled enterprise equipment when we did the layout and the distribution. However, that expansion space was sitting on a depressed slab, and so we are on a raised floor environment. So as I went through the discussions with the client leading up to the presentation, there were discussions about my non-disclosures and confidentiality agreements, and they basically said, "We want you to recreate everything and not use any of the documents from the project." So these are some rough sketches to kind of convey what it is that how the campus is laid out, how the facility is laid out. As I mentioned, we had a central plant. The data center is the first building off of the central plant, and then downstream of the data center, there's a lot of other stuff. There's office buildings, there's parking garages, there's testing facilities, there's all kinds of things downstream at varying degrees of redundancy and reliability requirements. We did get the engineers who designed the central plant originally to design the distribution system for concurrent maintainability. So we did have a redundant supply and return distribution system that went out that the data center connected into. Both are concurrently online at all times. So when we did the original design, it was one of those situations where the client had a campus under construction and they got partway through the design in the early stages of construction and had the epiphany that they had not provisioned themselves for a data center. And so we were given 3 months from the initial phone call until we had to deliver construction documents. And through that whole process, liquid cooling was never discussed. So the facility was never set up for it, never thought about. It was always understood that the HPC environment, the liquid cooled environment, would be at a separate facility. So we get that change of direction that came to us, and they said, we're bringing the HPC in, we're going to bring it in. Our generation 1 is going to be rear door heat exchanger. And what are we going to do with this? So at that time, I had recently transitioned to another firm, and I was brought in to be a subject matter expert for the design team through the early stages of design, where we were getting them up to speed with the campus distribution and the existing data center. The decision was made by the design team not to use CDUs in this application. They were looking at the water purity requirements and looking at the temperatures and said, nothing's required, we can go straight in. And the new ITE class was W2, actually has a design maximum operating temperature of 25 C, so just below the top end of the W2 range. So this kind of gives you an example of the layout of the facility as a whole. So there's 3 separate areas of the building. Each had their own concurrently maintainable loops. The first 2 portions of the building were all air-cooled ITE, perimeter CRAHs, as I mentioned. And then in kind of the light purple background here, this is where the facility was expanded mechanically into the core and shell space to add an extension of the concurrently maintainable loop and put in the rear door heat exchanger solutions. And then there was space left for 2 reasons. One was expansion, and the other that was for churn. So when they do tech refreshes, they wanted to bring the new HPC in, set it up, get it online, commission it, and then roll their load over to that new pod or module, if you will, before decommissioning the old system. So for those of you that were on at the introduction to the ACF group discussion 30 minutes ago, you'll recognize this slide. This is out of the ASHRAE TC 9.9 white paper on water-cooled ITE, showing kind of the different bits and pieces of a liquid-cooled, distribution and solution, where we have the facility water system, we have the technology cooling system, ostensibly separated by a CDU in many cases. In this one, the CDU was omitted, and so the facility water system actually went directly into the rear door heat exchangers. So after the end of this phase 1, where we brought in the rear door heat exchanger, the project encountered some challenges. The project encountered some challenges, and I was asked to come in and help them evaluate and resolve them. And so the first thing that we did was we sat down and did a comparison of the compute. So when I say capabilities air side, what I'm talking about here specifically are the ambient air requirements for the ITE, not talking about air-cooled equipment versus liquid-cooled equipment, but actually talking about the ambient air conditions that we have here. And so as you can see, for the most part, there is pretty decent alignment with the temperature, with the relative humidity, the altitude, the ambient air class, all these different key parameters that we typically look at. Dew point, this became a sticking point later on down the line. And in the previous discussion, we were actually talking about dew point and operating above dew point. And basically the air-cooled HPC, the RDHX HPC that was installed did not have insulation on the internal plumbing. And so the requirement was that if the chilled water supply temperature was colder than 2.2 C below the ambient air temperature, that we would need a preconditioning cabinet whose sole purpose was to dehumidify the air entering the ITE. You can also see over on the far right-hand column, technically they were trying to operate the HPC equipment slightly below what the catalog said for entering water temperature, but that had been resolved with the ITE manufacturer and approved. The water side is where things get interesting, and this is where we started running into some issues that I'll go into later. But you know, we talked about the chilled water supply temperature. The delta T, you know, they looked at the delta T and they said, well, you know, we're operating the existing chiller plant system at 8.3 C delta T, and our range is between 5 and 17 on the RDHX, so we're good to go. Let's move on down the lines, not talk about delta T. Get into the delta P. They never really looked at the delta P too closely, largely because the chiller plant was right, or the data center was right next to the chiller plant, and there was plenty of available DP. So they didn't really worry about it too much, said we're just going to balance the system and move on down the road. Nobody looked at the working pressure, and we'll talk about that here in just a second. The other part that comes into play when you're talking about the liquid-cooled ITE is the delta T, the transient delta T, the temperature rate of change of the liquid cooling loop as a function of time, and how that compares to the air-cooled systems. Right now, there's ASHRAE guidance on the air side temperature rate of change. There is not ASHRAE guidance on the liquids on the liquid supply temperature to liquid cooled ITE for that transient type situation, and so that's currently having to be looked at on a case-by-case basis for the solutions that are being provided and installed. So the design came out. You can see here it was all pretty well lined up. The air temperature was going to be 25 C. Everybody's happy with 25 C. Dew point of the space was being handled by a desiccant dehumidification air handler that was part of the base building design for the data center, but a preconditioner was required because the chilled water supply temperature at 5.6 C was greater than 2.2 C below the dew point of the space ambient temperature. And then on the water side, they kept it at the 5.6 C. The delta T's went through 2 generations of HPC in this build out, and you can see the delta T's are roughly double on the water side what it is for the air cooled. Because the air cooled part of the facility was not operating anywhere near design, it turned out that the actual building average going back to the chiller plant was not out of range. But we'll talk about that a little bit later as well. The key thing I want to hone in here on is the working pressure, and you'll see that the air-cooled servers were just shy of 1400 kPa maximum working pressure, and the HPC environment was just shy of 700 kPa maximum working pressure, and that's actually where the root of our problems were. So when we got into operation, you know, as I mentioned, the thermal compatibility issue, and I call this a thermal compatibility issue because of the fact that we had to do the preconditioning cabinets and whatnot. We lost floor space because the preconditioning cabinet is an additional cabinet that's not necessarily, you know, it's not doing anything really other than just dehumidifying the space. And if we had the facility operating at more compatible dew points, we would have recouped some floor space. Basically, the system was not optimized, but it was functioning thermally on the air side. The water side is where we had the bust. And where that bust came in was during normal operations, we didn't have any problems with the maximum working pressure. Where we had the problems was when the chiller plant was staging up and staging down chillers in response to the campus load. The pumps, as they would ramp up and down, were so big. These are 500 horsepower pumps. And the plant was set up with a very high makeup water pressure to it. During these transient events or during pump recovery from a power outage, we were seeing spikes in the actual working pressure on the chilled water supply side that was causing the HPC to go into a diagnostic fault and shut itself down. So we were having unplanned shutdowns of the ITE due to these pressure spikes in the chilled water supply system. The other thing that came up was the differential pressure that was required. So the campus is on a critical zone reset system. So it was basically resetting the pump control based on the most demanding building on the campus. And with the increased DP requirement for the HPC environment, we raised the building closest to the plant and have now become, in most conditions, the most demanding building on the campus for DP, which is affecting the overall building's energy consumption. And then the other big issue was the restart times after power failures on the chilled water pumps. Because of the size of the pumps, they were 4160 volt VFDs, 5 kV VFDs that took 10 minutes to restart after an outage. So when there was a full-blown power outage, the air-cooled ITE, because it was operating at lower loads and had thermal inertia in the system, in their coils and so on and so forth, didn't seem to have too much difficulty with it. But the liquid-cooled HPC was absolutely having issues shutting down because we didn't have thermal storage in there. There was no dedicated pumping to keep water moving while those 5 kV VFDs were going through their 10-minute restart. So we go into phase two. Phase two is we've got to fix the hydraulic issues from phase one, specifically the working pressure. We're adding more liquid-cooled ITE, more HPC compute, but this time we're going cold plate with CDUs. Again, the primary side of the new ITE had all the same water quality requirements as the existing system, so we were good to go there. So this is kind of what we were looking to do. We were taking that expansion space and we were plugging the cold plates into the expansion space and still retaining a little bit of space for IT churn and tech refresh. So compute comparison comes in here, and this is where things really start to get interesting with the liquid cooled. And some of the key things I want you to note on the liquid cooled is the temperature range is all compatible. The humidity range is all compatible. The dew point range is much higher. So with us not having forced air across the liquid cooled ITE, we no longer had to worry about the dew point situation. The other thing that came into play is that the solution that we were getting from the ITE manufacturer was from the CDU and its distribution piping all the way to the ITE. So it was a turnkey system. And in their operational setup, the TCS loop piping was not going to be insulated. As a result, we were actually going to have heat gain into the air in the data hall from the TCS uninsulated piping that was actually going to cause an airside load that we hadn't initially anticipated. Water side, we come in and we see a much higher water side delta T. And this is really what kind of started to trigger things for us when we were looking at what the proper solution was, is that this delta T on the water side was so high at 18.7 degrees C delta T. We're beyond the range that a chiller can handle in a variable primary flow setup. So we can't take that big of a delta T into a chiller and still have it run because we'll violate the operational requirements of that chiller. So airside, what we decided to do is we're going to separate the HPC from the campus plant. We're going to put in a dedicated high temperature loop that allows us to get rid of the preconditioner because we can raise our chilled water supply temperature now up to 21.1 C and move on down the road with that. The water side, again, we have these delta T's we had to worry about, but by separating the HPC environment from the air-cooled environment and decoupling that, we've given ourselves some freedom to work with. And you can see here that at 21.1 delta T, I'm sorry, 21.1 C entering, we're at 7 to 7.5 on the RDHX for a delta T, but we're all the way up at 21 degrees on the cold plate solution. So this is the high level schematic of what we ended up with. Now, the other part that I wanted to bring into this conversation, and it's why we went full bore with the separate chiller plant, not just separate chiller loops and a dry cooler and evaporative cooler solution, is we found out during the investigation that the chiller plant itself, the campus chiller plant, while it was designed originally to be concurrently maintainable, through some uninformed value engineering exercises that happened within that particular project's construction without consultation with the data center design team, the plant was actually built not concurrently maintainable. And we found a number of single points of failure. So we designed this chiller plant to be the primary source of cooling to the HPC, but also to be able to serve as the +1 to the air-cooled enterprise data center. So this kind of drills in a little bit on the high temperature plant, and we'll drill down one more time to a single side. And what you'll note here is that we've got the chilled water return coming back from the HPC on the left side, going through water side economizers, and then going through a set of heat exchangers, which for all intents and purposes are building level CDUs, and then going back into the HPC environment. That economizer runs directly off the cooling towers. That's an open loop cooling tower system, so water quality is not particularly good. So we absolutely had to make sure we segregated that. And then the chillers in the new plant are high temperature chillers, like I said, operating at about 21 degrees C. This time they're going through a thermal storage tank, and that thermal storage tank has enough buffer on it to handle the ride through of not only a power failure, but a power failure plus a couple of problems that may be encountered during that power failure. The key here is with that economizer. So, being in climate zone 2A, our typical outdoor, wet bulb temperatures are on the order of about 32 C, roughly speaking. And I'm sorry, not 32 C, 27 C. 28C, somewhere in that range. With the delta T that we have on the cold plate ITE, we were able to prove that all year round, even on an ASHRAE 20-year extreme condition, we are going to be able to economize the return water to some extent year round. So year round, we are getting some quote unquote free cooling off of the cooling towers. And then basically the chiller plant serves to trim cool us and get us down to the 21.1 C in the times of year where the cooling towers cannot handle the whole load. Here it is, an economizer operation. So you can see the simplified operation there. Thermal storage tank is out of the circuit, chillers are out of the circuit, et cetera. So the big things that we address with this design is the condensation being a big one, or the condensation risk being a big one. So we got rid of the preconditioning cabinets. We raised the chilled water supply temperature to get up above our space ambient dew point. We took care of the working pressure thing. We now have full control over the working pressure. We no longer have pumps that are sized to handle a multi-million square foot campus. We have pumps that are sized to handle a data center and HPE, and the pumps are explicitly selected to make sure that in the worst case failure condition, we do not exceed the maximum working pressures of the system. And then the required differential pressure. So we have now taken our HPC load and that very high differential pressure requirement completely off the campus. And we have now allowed this bank of 500 horsepower pumps to run at a lower supply differential pressure than they were running when they were hooked up to our HPC, saving quite a bit of energy for the client. And then the other big one is the chilled water pump restart times. Now, one piece of this, I mentioned that our design allowed the high temperature plant to serve as the +1 for the low temperature plant and the enterprise. It's actually set up so that if the large plant encounters a power failure, the high temperature plant will actually roll over and pick up the enterprise as well, so that the enterprise doesn't go through a transient condition that exceeds the limits. Obviously, energy efficiency is a big benefit here with the economizer running all the time. The chiller is running at a much higher efficiency. We went from chillers that are running at about 0.55 kW per ton of cooling to chillers that are running at about 0.125 kW per ton of cooling. We also chose to use oil-free chillers in this design, which allows the chillers to run in conditions where the condenser water is actually colder than the chilled water. So that gives us some flexibility during failure scenarios and whatnot. And then the long-term flexibility that it gives us. So W2 and W3 in this climate are some of the hardest systems to design around, because we have to be chiller-based part of the year and we can be economized other parts of the year, which has complexity and challenges on first cost, but it gives us a lot of flexibility down the line, so the client can maximize the efficiency gains if they put W3, W4, W5 equipment in the system or in the facility in the coming years. They can support that and leverage its full capabilities, or if their particular compute load and solution sticks around at W2, they can continue to operate there. Added resiliency, I touched on that for the enterprise piece. And then lastly here, our call to action. So those of you who were on at the introduction to prior to my my discussion here have already seen this, but basically we have weekly conference calls at 1600 London time, 1100 on the East Coast of the US, 0800 on the West Coast of the US. We're putting together reference designs, we're putting together guidance to help design these facilities and construct these facilities to try to give owners the ability to plug and play different water class and different topology solutions as best as possible going on down the line. And with that, I know we're right up at the end of the time. John Minash, do you want to, do we have any questions that have come in?
I'm not seeing any questions. Let me take a quick look here.
John Gross, I'd just like to say I always learn from your presentation. Cover a lot of bases. It intimidates me to use the word simplify, and after hearing a presentation like you gave, but I think we can boil down some lessons learned out of what you had and not replace the need for MEPs, but make sure that the MEP that does add stuff in the future as a simpler path, if you will.
Yeah, I mean, the end goal here is to give facility owners a simpler path and some guidance that they can use to help plan their facilities. It's to give a playbook for the MEPs that are doing the detailed design to help make sure that that owner's project requirement is met. And I will say that that the lessons learned that we got out of this project, particularly on the pressure side, the system pressure side of this discussion, are actually making its way into the ASHRAE TC 9.9 Thermal Guidelines version 5, which is currently in for final review before or for the committee before it goes to print. So previously, we've been looking primarily at the temperature side of this discussion. We haven't been looking too much at the pressure side of the discussion. And we're starting to get a more holistic view built into the thermal guidelines of the considerations that need to be accounted for when we're designing and operating these facilities.
Fantastic. I think we need to cut over to the panel discussion at this point. Is that about line up with the timing there, Michael?
I think it does.
It does. I think we're ready.
All right. Thank you very much, John.
Yep.
All right. So I'm going to